Alright, hello fellow sapiens. Sit back, relax, and prepare to step into a world where the sun once seemed to stop moving. Tonight, in the ancient science of light and stone, we'll explore how early humans learned to read the winter solstice long before myth, writing, or nations existed. This is slow science, quiet archaeology, storytelling for curious minds awake late at night. If you enjoy calm, factual journeys into deep time, a gentle like and subscribe helps other sleepless thinkers find their way here too. Tell me, where do you listen from? In bed, on a long drive, while working or studying? And if you drift off, timestamps in the description will guide you back when you return. Alright, let's continue, and as always, stay curious, stay calm. Now imagine standing at the edge of a world where nothing is artificial and nothing is measured, where the only clock is the slow turning of the sky. Picture a moment when early humans looked toward the horizon at dawn and noticed something strange. The sun, which usually shifted a little each day, no longer moved. For a handful of mornings each year the sunrise seemed to pause, rising from almost the same place as if held still by a quiet hand. We do not know for certain what they thought of this stillness, but the archaeological and environmental evidence suggests they recognized it long before they recognized anything else in the heavens. The winter solstice, with its brief halt in the sun's journey, became the first pattern that humans could reliably detect with nothing more than their eyes and patience. This was not yet myth or religion or even tradition. It was observation, the earliest form of science shaped by cold air, long nights, and the need to survive another season. To understand why this pause mattered, we must first understand what it looked like through the eyes of people living in the late Pleistocene, tens of thousands of years before writing. Their days were governed by daylight and their nights by fire. Each morning, those who woke before dawn could trace the first glow at the edge of the world and measure the sun's position against fixed features of the landscape. A mountain peak, a broken ridge, a scattered row of boulders, the silhouette of a distant cliff. These markers did not move, and in their stability they offered a quiet kind of information. Over the course of the year, the sun rose slightly farther along the horizon each morning. To see it change by even a small degree, one had to watch closely. But the human eye, trained by necessity and repetition, could do this without tools. What the archaeological record shows is that many Paleolithic shelters face particular directions, and some of these orientations match seasonal light patterns. It would be centuries before architecture turned this knowledge into stone, but even in this earlier period, people understood the horizon more intimately than we do today. In these winter weeks, however, the sun did something unusual. After drifting along the horizon for many months, its journey slowed until it seemed to stop. For 3 days in the depth of winter, its rising point shifted so little that it appeared fixed. This standstill is a natural consequence of the Earth's tilt and orbit, but the people observing it had no way of knowing that. What they did know was that everything around them was changing. The cold intensified. The animals they hunted shifted their routes or disappeared completely. The frost lingered on branches and stones longer each morning. Daylight shortened until life felt compressed into a narrow strip of time. The stillness of the sunrise coincided with the stillness of the environment, bringing a kind of tension that early humans could not ignore. We see traces of this tension in the remains of seasonal camps, in the storage pits of later hunter-gatherers, and in the careful positioning of certain dwellings toward the faintest light. Archaeologists sometimes describe this period as one of environmental pressure rather than dramatic crisis. But for people whose survival depended on the smallest changes in weather, it was pressure enough. The solstice was the moment around which food availability, mobility, and daily rhythms turned. While we cannot assign precise motivations to people who left no written record, we can examine seasonal migration patterns and see how movements across territories appear to cluster around periods of daylight shift. In many late Pleistocene regions, the winter months forced groups into sheltered valleys or areas with more predictable resources. Travelling at dawn or orienting oneself on open plains required attention to the horizon, and for those who moved seasonally, sunrise positions would have been among the most reliable cues they had. It is here that the early form of horizon tracking comes into focus. Every time people woke before the sun and looked toward the east, they watched not just for light but for direction. They saw how the sun slipped southward through autumn, then hesitated in winter, then slowly climbed northward again. This pattern, once noticed, would have been impossible to forget. There are caves in Europe whose entrances align with seasonal light angles, and while scholars cannot say with absolute certainty that these alignments were intentional, the consistency across regions is difficult to ignore. In studying these shelters, researchers have noted how engravings and paintings appear in areas shaped by specific light conditions, suggesting that early people were not only aware of seasonal changes, but were influenced by them in their daily lives. This pause of the sun offered something unique: predictability. Everything else in the late Pleistocene environment shifted with weather, climate, and migration, but the solstice returned with a precision unaffected by human decision. The earliest communities likely used this stillness as an anchor. We see evidence in the timing of the hunts, in patterns of communal gathering inferred from hearth sites, and in the seasonal deposition of tools and ornaments. Though it would be many thousands of years before these observations crystallized into monuments aligned to solstice sunrise or sunset, the cognitive foundation was already present. The solstice gave early humans a rare sense of structure in a world dominated by uncertainty. What is remarkable is how little was needed to notice it. No instruments, no mathematics, no settled life. Only the patient accumulation of daily experience. A person who took note of sunrise positions for 10 winters would understand a pattern. A community that passed this knowledge down for generations would eventually understand that the sun, at its weakest, stopped moving before returning stronger. This was the earliest hinge of the year, not because of what people believed, but because of what they saw. This solstice was not yet a story about rebirth or renewal. It was a threshold in the coldest season, a moment marked by observation and memory long before it took on symbolic meaning. For people who lived entirely by the sky, that stillness was the first reliable hinge of the year. To understand how they used it, we must step into the deeper darkness of early winters. Even in regions far from dramatic winter extremes, the solstice's pause would have been perceptible to those who relied on early morning light to organize their movements. In open plains, where the horizon stretches without interruption, a sunrise that refuses to shift becomes even more striking. Archaeologists studying Pleistocene mobility have noted how often camps change orientation throughout the year. These subtle rotations suggest an awareness of seasonal light angles, as people continually adjusted where they slept, where they cooked, and where they placed their fires. Such choices were likely practical, tied to warmth and wind, yet they also shaped a habit, looking toward the same point on the horizon every morning. Over years of repetition, recognition grows not from theory but from rhythm. The sun's small hesitation in winter would have been part of that rhythm. Notice the way a hunter notices the absence of footprints, or a gatherer notices the first signs of thaw. There is another layer to this observation that does not survive in artifacts but survives in patterns. During the late Pleistocene, the sky was the most consistent backdrop for teaching. Skills were transmitted verbally, but orientation was taught visually. A child might learn the path to a seasonal water source by following the sun's direction, at a particular time of morning. They might learn where certain animals travel by the angle of light falling into a valley. Because of this, many researchers argue that early sky watching was woven into daily movement, rather than reserved for special moments. The solstice would expand from a single observation into a period of awareness, a time when the change in daylight slowed enough for even inexperienced observers to notice. This recognition likely spread across generations not as doctrine, but as a simple fact repeated often enough to become common knowledge. The stillness of midwinter light also brings with it a quality that archaeologists call atmospheric orientation. In deep winter, when the ground reflects little warmth, the air becomes visually clearer. Fog forms differently, shadows sharpen, and distant ridges stand out against pale skies. This clarity makes small changes on the horizon easier to detect. Ethnographic studies of indigenous groups who still watch the sky without instruments suggest that cold season light can be more revealing than any other time of year. If similar conditions held in the Pleistocene, then the solstice may have been the easiest astronomical event to perceive with consistency, giving it a reliability unmatched by the movements of stars or the phases of the moon. Taken together, these clues suggest that early knowledge of the solstice did not come from a single revelation, but from generations of watching the same horizon through the coldest months of the year. It was an understanding built slowly, the way a path through a forest becomes clear only after many feet have walked it, and so the solstice became the first stable reference point in the human relationship with the sky, a moment when time felt anchored in place rather than drifting. For people who lived entirely by the sky, that stillness was the first reliable hinge of the year. To understand how they used it, we must step into the deeper darkness of early winters. A small band of humans walking across a late Pleistocene plain, feeling the daylight thinning faster than their preparations can keep up. Each evening arrives sooner, each morning later, and the hours between offer less warmth than the day before. There are no clocks and no written calendars, but the diminishing light presses against the edges of their awareness with a clarity that requires no instruments. What happens when the world darkens faster than a community can prepare for it is not remembered in stories or symbols from this distant age, but it is preserved in something older than writing. It is found in the bones of animals, in the pollen trapped in sediment cores, and in the patterns of seasonal settlement left behind by people who lived at the mercy of winter's advance. The evidence suggests that declining daylight in the late Pleistocene was not simply an astronomical curiosity. It was an ecological warning, sharpened by hunger and cold, long before anyone transformed it into ritual or story. Winter was not a poetic season then, it was a threat. When archaeologists examine faunal assemblages from Paleolithic sites, they often find patterns that mirror this threat with unsettling precision. During the coldest months of the last glacial periods, large herbivores migrated along routes that shifted dramatically with the seasons. Reindeer, horses and steppe bison often moved away from exposed plains to areas with more reliable vegetation. Hunters who depended on these animals tracked their absence as carefully as their presence. Cut marks on bones and butchery sites reveal that midwinter kills were rarer than those in autumn, a pattern repeated across regions stretching from Iberia to Siberia. This scarcity tells us something important. Early humans did not need abstract astronomy to understand the danger of shortening days. They saw it in the empty trails, the thinning herds, and the growing quiet of landscapes once filled with hoofbeats. Darkness in this context was not symbolic. It was the absence of food walking slowly across the horizon. Plant availability followed an even harsher rhythm. Paleo-environmental cores taken from lakes and peat bogs show a clear reduction in edible plant species during the coldest phases of the year. Grasses retreated under snow, leaves withered, and stored tubers became more difficult to access. People who relied on seasonal gathering faced a narrowing window in which to prepare. Sites from the Gravettian and later Upper Paleolithic reveal storage pits containing preserved seeds, dried roots, and crushed vegetal material that may have been processed to last through the darkest period. Though these pits differ across regions, their timing aligns with the contraction of daylight recorded in climate proxies. This suggests that winter was not merely a time of waiting, but a time of active, urgent preparation. The diminishing light signalled the beginning of that urgency. One of the clearest indicators of winter pressure comes from what archaeologists call emergency fat storage strategies. In many Paleolithic sites, kill patterns shift toward targeting animals rich in fat just before winter sets in. Reindeer males entering the rut lose much of their fat, but females retain valuable reserves deep into the cold months. Hunters selecting more female reindeer toward the end of autumn suggests strategic decision-making based on energy needs. In return, bone marrow extraction marks become more frequent, indicating that people processed carcasses with painstaking attention to recover every calorie. Chemical studies of burned bones at some Upper Paleolithic sites show that fat rendered from marrow and bone grease became an essential resource during the long nights when plant foods vanished and fresh kills became unpredictable. To understand this behaviour is to understand how intimately daylight and diet were linked. The solstice, with its shrinking hours, was not an abstract idea. It was an ecological boundary. Seasonal weather changes recorded in paleoenvironmental cores from multiple continents trace the onset of winter with similar clarity. Layers of wind-borne dust increase during the darkest months, revealing periods of stronger winds and colder temperatures. Ice cores from Greenland show changes in isotopic composition that align with shifts in global climate cycles. While early humans had no knowledge of these large-scale processes, they lived at their edges. They felt the sudden drop in temperature, the way frost formed earlier than expected, and the way water sources froze before new routes could be established. Sediment cores, rich in microscopic plant remains, show how dry season grasses dominated some landscapes during glacial winters. These changes shape the timing of movement, pushing groups to relocate earlier or settle closer to sheltered areas where water and fuel remained accessible. Mobility in this context was not freedom but necessity, governed by daylight rather than desire. The link between daylight and movement becomes even clearer when examining patterns of seasonal migration routes. Archaeologists studying the distribution of temporary sites across river valleys and plateau edges have noted how frequently the direction of winter travel correlates with access to morning light. Groups often move towards southeastern slopes where sunlight reached the ground first, warming frost-hardened soil and allowing earlier foraging or hunting. This subtle orientation is not decorative, it is practical. A few extra minutes of warmth could determine whether children survived the coldest weeks. A few extra minutes of light could determine whether hunters returned before darkness made the landscape dangerous. By shifting their mobility based on daylight constraints, early humans responded to winter's threat in a deeply embodied way. The solstice was, for them, less a date than a signal that movement had to be recalibrated. We do not know how consciously people of the late Pleistocene connected their biological needs to the astronomical cycle of decreasing daylight, but the archaeological evidence suggests that awareness came first from hunger, cold, and the exhaustion that comes from short days when work must compress into narrow windows. The solstice likely emerged as an ecological alarm long before it became a moment of anticipation or ceremony. When people noticed that the light reached a minimum and that the days ceased to shrink, it may have offered a kind of reassurance that the worst point had been reached. Even without ritual or symbolic meaning, that turning point held weight. It marked the threshold between scarcity increasing and scarcity easing. It was a hinge not because of belief, but because of survival. As we trace these patterns across bones, pollen, isotopes and hearths, left long extinguished, we begin to understand that early knowledge of seasonal change arose not from curiosity, but from necessity. The solstice mattered because winter threatened faster than preparation could keep up. And once early humans learned to predict this turning, once they recognized the solstice not as an arrival of darkness, but as the beginning of its retreat, the relationship between people and the sky changed forever. The moment people could predict that alarm, everything changed. Picture a moment when people who had never seen a written symbol stood at the mouth of a cave and realized that the sun would rise tomorrow in almost the same place it had risen the year before. There were no calendars to consult, no carved markers to check against, only the long, patient memory of a community that had watched the horizon through more winters than any one person could remember. Yet somehow, in the Upper Paleolithic, humans learned to predict the darkest day of the year with a precision that still surprises researchers. They did it not through abstract mathematics or ritual devices, but through the oldest scientific instrument on Earth, the landscape itself. Mountains, ridges, valleys and notches formed a fixed geometry that returned each year, offering a stable backdrop against which the sun's slow drift could be learned. By watching where light first touched these features, people began to understand when winter reached its turning point. We do not know for certain how consciously they recognized this cycle, but the evidence suggests that their observational skills were developed through necessity and sharpened by time. Some of the earliest hints of horizon tracking appear at places like Lascaux in southwestern France, a site better known for its animal paintings than for its relationship to the sky. Yet several chambers and passages align closely with solstitial and seasonal light angles, a pattern difficult to attribute entirely to chance. These alignments are subtle, a shaft of evening light entering a particular alcove in late winter, or the way dawn might illuminate upper walls only during certain weeks of the year. Lascaux is not the only example. Across Europe, Ice Age shelters show orientations that appear favoured not simply for protection, but for the direction they faced. Archaeologists examining these dwellings have noted how often their entrances correspond to specific sunrise or sunset points when mapped against reconstructed Pleistocene horizons. These observations, while still debated, suggest that early humans were not simply painting in caves, but were choosing locations in part because of how light interacted with stone. For people living millennia before agriculture or permanent settlements, such choices reflect an awareness of the sky that predates formal structures by thousands of years. Landscape features provided the first reliable calendar in this world of shifting climate and uncertain seasons. A mountain peak that the sun touched only in midwinter, a cleft between hills where the first light emerged each autumn, or a solitary boulder on the horizon that aligned with the sunrise only once a year could all serve as temporal anchors. These features did not move. They endured beyond the life of any hunter or gatherer, offering continuity across generations that few other environmental elements could match. Ethnographic studies of indigenous groups who still rely on horizon watching show similar practices. The position of the sun against a specific ridge or tree line marks seasonal changes far more reliably than counting days. In some regions, the first morning when the sun touches a particular rock signals the beginning of migratory preparation. In others, the point where shadows fall in late afternoon indicates the turn of a hunting season. These parallels do not prove that Upper Paleolithic groups acted the same way. but they provide a window into what horizon science looks like in societies rooted in direct observation. Repeated engravings found on portable objects from the Upper Paleolithic add another layer to this picture. Some small bones and antler pieces contain sequences of notches or repeated marks that scholars have interpreted as rudimentary tallies of seasonal changes. The interpretation remains cautious, yet these patterns often appear in numbers that correspond loosely to lunar or seasonal rhythms. A series of 29 or 30 marks carved into a fragment of mammoth ivory may record the passing of days in relation to moon phases. Other sequences appear grouped in clusters that suggest cycles rather than counts, possibly relating to the arrival of cold seasons or the timing of certain migrations. While we cannot claim these engravings represent early calendars, the deliberate repetition indicates a growing interest in tracking time. Combined with horizon observations, they hint at a cognitive shift toward prediction rather than reaction. Humans were no longer merely responding to seasonal change, they were beginning to anticipate it. Ethnographic analogues reinforce this notion. Among communities from the Arctic to the Andes, horizon-based skywatching remains deeply integrated into subsistence strategies. Hunters track the angle of sunrise to determine when certain animals begin seasonal movement. Gatherers monitor the length of dusk to estimate when particular plants emerge. These practices require no formal astronomical knowledge, only repeated exposure to the land and long-term memory passed from elder to child. The parallels suggest that early humans could have easily developed similar strategies, especially as their populations became slightly more stable during the later Upper Paleolithic. Seasonal aggregation sites show that some groups return to the same locations year after year, building a body of local environmental knowledge far deeper than what highly mobile ancestors could maintain. Settlement stability, even brief or partial, allows the slow accumulation of sky-based wisdom. This stability becomes particularly visible in regions where caves and rock shelters show repeated occupation across centuries. Each group arriving in the same shelter would inherit not only the benefits of its protection, but also the knowledge attached to its position. If the cave entrance faced a sunrise alignment recognizable only at midwinter, then each generation would encounter the phenomenon at roughly the same time in their lives. The durability of the landscape becomes a silent teacher, anchoring the sense of seasonal timing through repetition rather than instruction. As this cycle continues over many centuries, the ability to predict the solstice moves from an individual skill to a shared communal expectation. It is no longer merely a surprise when the days cease shortening. It becomes something known in advance, learned through watching the same ridgeline over and over. We often imagine ancient humans as lacking the tools to engage with astronomy, but what the archaeological record shows is that tools were unnecessary. Patience, memory, and familiarity with the land provided more than enough information to anticipate the solstice. This prediction was not mystical. It was empirical, created by countless hours spent watching where light fell each morning and how it moved across the horizon through the seasons. This solstice became predictable not because people created stories about it, but because they built a long-term relationship with the land and the sky. The result is a form of science grounded in experience rather than abstraction, a knowledge system created through continuity rather than calculation. Once prediction existed, measurement began. Another piece of this early horizon science becomes visible when we consider how the human eye and memory work together in open landscapes. In regions where snow covered the ground for long stretches, the contrast between dark ridgelines and bright sky made the sun's movement easier to perceive. Even a slight shift in sunrise position becomes more noticeable when the world is stripped of colour and texture. cold season clarity sharpens edges and reveals the smallest topographic irregularities. Researchers studying Ice Age ecology have observed that winter visibility often extended for dozens of kilometres, giving observers an uninterrupted view of the horizon. This kind of optical reach created a natural laboratory for sky watching, where even a single degree of solar movement could be detected by someone who watched the same ridge every morning. When combined with slow seasonal changes, these environmental conditions created perfect circumstances for developing long-term visual memory tied to the land. Another factor that strengthened this memory was repetition across generations. In the Upper Paleolithic, groups often returned to the same shelter or valley year after year. This cyclical movement meant that children grew up learning the horizon as part of their environment, not as a separate scientific pursuit. An elder pointing to a distant peak and saying, "When the sun rises there, the cold deepens," is not preserving ritual. They are transmitting a practical observation encoded in place. As those children grew and passed the knowledge along in turn, the ridge became more than a feature. It became a reference point that lived through time, carrying the weight of accumulated observation. Archaeologists call this phenomenon ecological inheritance, where a community inherits not only a landscape, but the knowledge attached to it. The engravings found on bone and antler pieces add another dimension. Some show repeated marks arranged in patterns that suggest periodic monitoring. While theories remain cautious, a few pieces exhibit subtle changes in mark spacing, as though tracking intervals rather than simple counts. This may reflect an early attempt to capture rhythm in material form. The idea is supported by experimental archaeology, showing that even untrained individuals begin tracking cyclical events simply by recording them in repeated sequences. When viewed alongside horizon alignments, these artifacts suggest that people were not just observing cycles, but experimenting with ways to preserve them outside memory. This is not yet formal notation, but it is a step toward externalizing time. Environmental consistency also played a role in shaping early predictive knowledge. Even in the unpredictable climates of the late Pleistocene, the solstice remained one of the few stable celestial events. Its alignment with the same fixed features each year gave early humans a steady point in a world dominated by change. In archaeological contexts, we often focus on the dramatic transitions, glacial advances, rapid warming events, sudden migrations. But beneath these shifts, people tracked the dependable movements of the sun. The landscape may have altered slowly over millennia, but within any given human lifetime, it was stable enough to serve as a reliable guide. This stability allowed prediction to emerge not from calculation, but from awareness that the same pattern returned. Taken together, these elements reveal a form of early science rooted in the land itself. Horizon prediction offered a baseline around which survival decisions could be organized. It allowed communities to anticipate not just the arrival of winter's peak, but the moment it would begin to recede. In this way, the horizon transformed from a distant boundary to a tool, one that linked memory, observation, and movement. Once prediction existed, measurement began. Imagine a moment when someone stepped into a cave not to escape the cold or to rest after a long hunt, but to watch how a thin blade of winter light touched the wall. There were no calendars or written systems to guide them, only the memory of how far that light had reached the year before. Picture a cold dawn in the Upper Paleolithic, when the air outside the cave entrance held the quiet density of deepest winter, and the sun rose at its southernmost point. A single shaft of light entered the darkness, illuminating a patch of stone that remained untouched for the rest of the year. What compelled early humans to carve the sky into marks on stone may never be fully known, but the evidence suggests that the first attempts at measurement grew from this interplay of darkness and light. In the depths of caves that were otherwise shrouded in shadow, early people created abstract notations that may represent the earliest physical attempts to record celestial cycles. We do not know for certain whether these marks were intended to capture the solstice specifically, but their placement, repetition, and orientation point toward an emerging desire to measure time itself. The cave of Lascaux offers some of the clearest insights into this early experimentation. Although the cave is famous for its complex paintings of animals, the orientation of its entrance has drawn increasing attention from archaeoastronomers. The structure of the cave's main axis and the direction of its south-facing entrance allow the low winter sun to cast controlled light into specific chambers. Light studies conducted with reconstructed models of the cave show that certain parts of the interior are only illuminated when the sun approaches its lowest annual arc. These patterns of illumination are not incidental. The geography of the entrance and the internal layout create predictable corridors of light that shift subtly at specific times of year. For people living tens of thousands of years before formal settlements, such natural illumination would have offered a visual cue unlike any other. The cave itself became a kind of observatory where the solstice could be recognized not by looking out at the horizon, but by watching how light behaved within stone. Even more intriguing are the repeated abstract symbols found inside many Paleolithic caves, including Lascaux. These include sequences of dots, lines, and geometric shapes placed in areas where seasonal light could reveal or obscure them. Some appear beside or below animal figures, though they do not mirror the forms of those animals. Others appear in clusters that seem to follow a rhythm. Scholars studying these marks have proposed that at least some may represent attempts to note seasonal intervals. While these interpretations remain provisional, the placement of such patterns in chambers that brighten only around midwinter strengthens the possibility that they served a temporal purpose. It is one thing to carve an image into stone. It is another to place that carving in a spot that becomes visible only at a specific time of the year. This intentional relationship between symbol and illumination hints at a cognitive shift. People were no longer only observing the solstice through the horizon. They were beginning to record its timing inside the earth. Experiments with firelight in Paleolithic reconstructions offer further clarity. Researchers have reenacted torchlit journeys through caves to study how carvings, paintings, and engravings respond to shifting light. In some chambers believed to have held seasonal significance, flickering firelight transforms the appearance of repeated marks, revealing them more clearly or causing them to shimmer as though animated. This suggests that early humans understood how to control and manipulate interior light to create specific visual effects. The controlled use of firelight in these contexts implies deliberate experimentation with illumination. If people were already familiar with how sunlight entered the cave at predictable times, firelight could have served as a tool to study and reinforce those observations during the darker months. It is in these dim conditions that the first seeds of measurement appear, not through numbers but through these controlled interplay of light and shadow. Comparative analysis across multiple Paleolithic sites adds weight to the idea that the placement of symbols and paintings was not random. In caves such as Altamira, El Castillo, and Chauvet, clusters of abstract marks appear in similarly light-sensitive locations. These locations often remain dark throughout most of the year, yet become partially illuminated when the sun reaches particular seasonal angles. This pattern repeats across regions separated by hundreds of kilometres, suggesting a shared conceptual framework even among groups that never communicated directly. Archaeologists remain cautious about attributing astronomical intent to these orientations, but the statistical likelihood of repeated region-wide non-random placement is difficult to ignore. a pattern that emerges independently across many cultures, often reflects a practical solution rather than coincidence. In this case, the solution appears tied to marking, recalling, and anticipating seasonal change. To understand why people might carve marks into stone while standing in darkness, we must consider what the solstice represented at this stage of human development. Before it became tied to myth or social gathering, the solstice was a turning point in lived experience. It marked the slow return of daylight and the easing of environmental pressure. Making marks in the cave allowed early humans to connect this turning point with a fixed place. The interior offered stability unlike the open landscape. Its walls did not erode quickly, its darkness did not shift with weather, and its structure provided a physical memory that did not depend on human recollection alone. An engraved line in stone could outlast its maker, serving as a bridge between generations who needed to know the same information. In this way, the solstice became not just an observation but an anchor, something that could be recorded, revisited, and transmitted. What emerges from these patterns is an early form of cognitive geometry. Without formal mathematics, early humans recognized the relationship between angle, distance, and illumination. They learned how light entered a fixed space and how that entry could mark a recurring moment in the year. Carving the sky into stone was not an act of abstraction for its own sake. It was a practical attempt to externalize time in a medium that did not fade. In the long sequence of human intellectual history, this may be the first moment when people began to record a repeating astronomical event deliberately. The solstice was the first moment humans tried to record, not because it was mystical, but because it was stable. It returned every year, touching the same walls, revealing the same marks. Through these marks, humans discovered that time could be made visible. Millennia later, this geometry moved outside into open ground. Another dimension of this early measurement emerges when we consider how caves protected information that the open world could not. Outside, snow cover, shifting vegetation, and migrating herds constantly altered the landscape. But inside a cave, the walls held their shape for thousands of years. A mark placed at a particular height or orientation remained stable long after its maker was gone. This stability allowed early humans to experiment with encoding not just images but intervals. One small engraving found in a secondary chamber at Lascaux shows a short cluster of vertical incisions unusually close to an area that receives weak midwinter light. These incisions are separated into uneven groups, suggesting that they may not represent counts but segments of time. Their function remains uncertain, but the clustered arrangement implies an intention beyond decoration. When archaeologists ran light simulations on the chamber, they noticed that certain clusters become visible only when the sun reaches its lowest angle of the year. The potential connection between visibility and timing provides one of the earliest glimpses into humans using controlled light to make an abstract concept concrete. Other caves across Western Europe show similar relationships between engravings and illumination. In the cave of La Pasiega, geometric signs appear in narrow corridors where sunlight never enters, but where firelight reveals their shapes distinctly. This separation of symbol from natural light may reflect an attempt to create a reference point independent of seasonal illumination. Scholars who study these locations argue that combining sunlit markers with firelit ones suggests an early developmental stage of timekeeping that uses different types of light to indicate different phases of the seasonal cycle. If this interpretation holds, the presence of both fire-revealed and sun-revealed markings could represent an early dual system of tracking time, one used for daily or ritual access, and another for larger astronomical intervals. In some caves, researchers have identified niches and alcoves where soot residue accumulates predominantly during a narrow range of years. These pockets of repeated activity hint that certain parts of the cave were visited seasonally with remarkable consistency. When excavated, these areas often contain charcoal fragments, with radiocarbon dates spread across centuries. This pattern suggests that groups return not randomly, but at specific points in the year, perhaps timed by the predictable behaviour of light entering the cave. Such repeated visits would have reinforced the relationship between the physical structure of the cave, the predictable path of the sun, and the marks left behind. Over time, these return patterns would condition communities to think of certain spaces as time containers, places where the year could be read not by the horizon but by the walls themselves. This early use of caves as mnemonic structures appears even more remarkable when we consider the cognitive leap required. Instead of relying solely on memory or oral instruction, early humans began placing knowledge into the environment itself. This is what cognitive archaeologists refer to as environmental scaffolding, a process in which the physical world becomes a partner in human thought. By engraving marks in places where light behaved predictably, people created an external structure to hold time steady. The solstice, as the most stable astronomical moment they knew, naturally became the reference point around which these early structures formed. Even without conscious intent to measure, the persistent interaction between light and stone would have created a feedback loop. The return of solstice light revealed the same marks every year, teaching each new generation when the cycle had reached its turning point. Through these quiet experiments, measurement in darkness began to take shape, not as a system imposed on nature, but as one discovered within it. The cave walls became surfaces where time could be seen, recalled, and eventually anticipated. And once people realized that a moment as intangible as the solstice could be anchored in stone, they carried this knowledge outward into landscapes far beyond the reach of a single beam of winter sun. Millennia later, this geometry moved outside into open ground. Picture a moment when the winter sun rises in a place chosen not by the land but by people. Imagine standing on a cold plain in Central Europe 5,500 years before the Common Era, where a ring of timber posts surrounds you like ribs of an enormous wooden circle. The night has been long, and the frost is still thick on the grass. As dawn approaches, a narrow opening in the eastern palisade frames a strip of pale sky. People gather silently, wrapped in hides, breath rising in clouds. The sun lifts, not behind the nearest hill or the most obvious ridge, but precisely within that slit of wood. For the first time in European history, the solstice sunrise passes through a doorway designed specifically to hold it. What compelled early farming communities to build these circles in the snow for a single sunrise remains partly mysterious, but the archaeological evidence reveals one unmistakable truth. The solstice had moved from horizon to architecture. Gossec, and other early circular enclosures like it, represent a new stage in human cognition, when the sky became something that could be shaped through design. Gossec, discovered in the late 20th century, is one of the oldest known solar observatories in Europe. Its construction dates to the 5th millennium before the Common Era, a period when farming villages and early pottery cultures spread across Central Europe. The enclosure consists of concentric rings made of palisades and ditches, each pierced by carefully positioned gates. The eastern and western gates align with the extremes of the winter solstice sunrise and sunset, a precision unlikely to be accidental. When archaeologists mapped the post holes, they found that the sightlines created by these gaps matched the solar positions at midwinter with remarkable accuracy. To create such a structure required not only knowledge of the solstice, but a deliberate intention to embed that knowledge into wood and earth. Where earlier communities learned the solstice through the slow observation of landscape features, people at Gosek chose to reshape the ground itself, building a geometry that recorded what had once been found only at the horizon. The arrangement of post holes at Gosek shows an attention to detail that suggests a sophisticated understanding of visual alignment. The palisade stood several meters high, creating a controlled viewing environment that blocked out irrelevant parts of the sky. The eastern gate, narrow and steep-sided, framed the rising sun at its lowest annual point, while the western gate held the setting sun in a similar corridor of sight. These constructions created an artificial horizon inside the enclosure, a controlled space where observers could witness the solstice without relying on distant mountains or unpredictable weather conditions. The engineering reflects a cognitive transition. People were no longer merely watching the solstice, they were capturing it. Alongside the solar sight lines, archaeological evidence inside the enclosure strengthens the idea that these circles served calendrical and ceremonial purposes. Excavations revealed pits near the gates containing burnt materials, including bones and charred organic matter. The presence of burnt offerings, while interpreted cautiously, points toward activities timed with the solstice. These deposits are concentrated near the eastern gate, implying that the moment of sunrise carried particular significance. Whether these offerings symbolized renewal, gratitude, or preparation for the coming year remains unknown, but their association with the solstice alignment suggests that the event had become part of the community's seasonal rhythm. The solstice was no longer simply a turning point recognized through hunger or landscape, but a moment marked through intentional acts. Evidence from surrounding settlements adds context to these gatherings. Archaeologists have identified clusters of dwellings near Gosek that show seasonal occupation patterns. The distribution of pottery, tools, and animal remains suggests that people gathered near the enclosure during the winter months rather than living there year-round. This implies a deliberate movement toward the site during the solstice period. Seasonal gathering has deep roots in European prehistory, but Gosek represents a more formalized expression of this behavior. Instead of meeting in a valley or at a riverbank, communities met at a constructed place where the sky itself became part of the gathering. The structure turned the solstice into a shared event, something witnessed collectively rather than understood individually. The enclosure created a communal frame for returning light. Technological continuity connects Gosek to earlier timber circles in the region. Although smaller and less precise, earlier structures show similar patterns of circular design and controlled entrances. These earlier circles, some nearly 2,000 years older, lacked clear solar alignments, but demonstrate an architectural interest in symmetry and enclosed space. Gosek represents the moment when these traditions converged with astronomical knowledge. It stands at the intersection of inherited building techniques and newly refined skywatching skills. The transition from simple gathering spaces to solstice-aligned architecture was not sudden. It was the result of generations of accumulated environmental knowledge applied to increasingly structured design. When we consider all these pieces together, the sightlines carved through wood, the burnt offerings near the gates, the seasonal return of nearby communities, and the architectural continuity across centuries, a picture emerges of a society beginning to formalize time. The solstice became something fixed not only in memory or in the behavior of the land, but in the built world. The circle in the snow was both a marker and a meeting place, a physical anchor for a moment that had long governed survival. For the first time, humans shaped the landscape to hold a single sunrise steady. The solstice moved from observation to architecture, from horizon to human-made design. But in another region, the same shift had begun even earlier. Another layer of complexity in sites like Gosek becomes visible. when we look at how people manage the materials themselves. The carpentry required to construct a palisade circle of this scale in the 5th millennium before the Common Era implies a coordinated workforce and advanced timber knowledge. Each post had to be trimmed, shaped, carried, and planted at a consistent depth, and the spacing had to be tight enough to control the line of sight, yet wide enough to maintain structural integrity. The effort suggests communal planning rather than the work of isolated individuals. Archaeologists analysing the tool marks on surviving post moulds have identified repeated patterns consistent with shared techniques, hinting that specialised skills were developing within these early farming communities. The solstice alignment was therefore not an incidental byproduct. It was supported by an emerging social organisation capable of executing complex architectural tasks. The circular form of Gosek also speaks to the symbolic and practical utility of geometry itself. While we cannot project modern mathematical concepts onto Neolithic builders, the consistency of radius, curvature, and partitioning indicates that people were thinking spatially in new ways. The ditch surrounding the palisade follows a near-perfect arc, demonstrating an understanding of how to maintain spacing over long distances. This would have required some method of marking or pacing the ground, perhaps through repeated steps or simple chords. When combined with the carefully aligned gates, the enclosure reflects a growing ability to impose ordered shapes onto the environment. The solstice thus catalysed not only architecture but early geometry. Another clue to Gosek's role comes from its position in the broader landscape. The enclosure sits on a gentle rise with clear views of the eastern and western horizons. Surrounding fields show evidence of early agriculture, including carbonised grains and storage pits for winter food. This suggests that Gosek was not isolated, but integrated into a network of subsistence activities. The solstice may have marked a moment that connected agricultural cycles with social gathering. If winter was the time when farming paused and stored resources were consumed, then a midwinter gathering around a solstice-aligned structure may have served both practical and communal purposes. It could have been a time to redistribute food, renew social bonds, or coordinate future activities in anticipation of the returning light. While these interpretations remain cautious, the archaeological pattern of settlement proximity supports the idea that the enclosure functioned as a focal point during the coldest season. There is also evidence that the circle was maintained and modified over time. Post holes exhibit multiple construction phases, with some posts replaced or repositioned. This continuity suggests that the importance of the place persisted across generations. A site that receives repeated upkeep is one that carries meaning beyond its initial construction. The solstice alignment, once established, became part of the identity of the community. The circle served not only as a functional observatory, but as a repository of shared memory. Each new generation inheriting the structure would have learned to read the gates the same way their elders had, creating a lineage of knowledge tied to a specific point on the land. By studying these layers of design, labour and continuity, we see how early farmers transformed a celestial moment into a physical anchor for social and cognitive life. The Gosek Circle is not merely an architectural curiosity, it represents a profound shift in how people related to the sky. They no longer waited for the solstice to reveal itself. They built a structure that ensured it would be seen. But in another region, the same shift had begun even earlier. Imagine standing on a high limestone plateau long before cities, metallurgy, or fields of grain reshaped the human world. The air is cold, the vegetation sparse, and the horizon nearly open in every direction. It is early in the 10th millennium before the Common Era in what is now southeastern Turkey. The communities who gather on this plateau do not plant crops or raise animals yet, but they carve stone pillars with extraordinary skill. shaping them into enclosures that seem to echo a plan held in the mind rather than the land. And as the midwinter sun rises lower each year, its light spills through certain openings between pillars in ways too precise, too consistent, to be accidental. What compelled early humans, thousands of years before agriculture, to design a solstice marker without the tools or technologies we often associate with sophisticated engineering? The revelation comes from ongoing excavations at Karahan Tepe, a sister site to the more widely studied Göbekli Tepe. Though still emerging from the earth, the architecture of Karahan Tepe shows patterns that suggest intentional alignments towards solar points, including the position of the winter solstice sunrise. The idea remains under careful review, but several archaeologists analysing its orientation have noted alignments that converge around midwinter light. If confirmed, Karahan Tepe would demonstrate something profound. The solstice was not a farming invention. It was already a compass for early builders in Southwest Asia, long before the first domesticated grain. The first clue lies in the general orientation of several enclosures at the site. Many are oriented in directions that do not respond to topography, water access, or defensive advantage. Instead, the axes of some structures correspond to positions where the sun appears at specific points in the year. In certain excavated buildings, the entrance corridors frame views of the eastern horizon. When researchers reconstructed the likely height of surrounding walls and pillar spacing, they noted that midwinter sunrise would have fallen directly within these narrow passageways. Such orientation is unlikely to result from chance, especially given the complexity of the site's design. These builders selected where the light would travel, shaping the opening not merely as an entrance but as a visual guide. Inside the enclosures, the pillars themselves play a role in controlling light. Many of them stand in symmetrical patterns, but with slight deviations that create narrow paths for sunlight to enter. Their surfaces, carved with animals and geometric motifs, catch and reflect light differently across the year. Experimental work using three-dimensional models and light simulations suggest that certain pillar shadows lengthen, overlap, or retreat in distinctive ways at midwinter. Pillar placement, therefore, may have been more than decorative. It may have functioned as a silent indicator of the sun's position, transforming the interior of the structure into a living instrument that displayed the changing season through shifting patterns of light and shadow. We do not yet know for certain, but the evidence suggests that the builders were creating a controlled light environment to reveal the returning sun at its weakest moment. The floor features of Karahan Tepe add another layer to this possibility. Excavations revealed carved channels, shallow basins and depressions, whose placement correlates with angles of seasonal illumination. In one building, a basin receives light for only a few days around midwinter, while remaining in shadow during all other times of year. This narrow illumination window suggests intentionality. In environments without written calendars, such features may have acted as annual indicators, marking the point when the sun began its slow ascent. Observers standing inside the enclosure could watch the beam of sunlight advance or retreat across the stone floor, eventually striking a feature that signalled the turning of the year. These interactions between stone and light represent some of the earliest known attempts to bind astronomical events to architectural form. Comparisons with Göbekli Tepe provide an instructive contrast. Göbekli Tepe, though roughly contemporaneous, uses a different strategy. There, many enclosures are oriented more variably, and some appear aligned towards stellar targets rather than solar ones. This variation does not diminish the significance of either site. Instead, it illustrates that communities across the region experimented with different ways of integrating the sky into architecture. Göbekli Tepe's builders may have been concerned with night sky events or constellations, while Karahan-Tepes may have favoured the rhythm of the sun. The differing strategies do not signal cultural division but creative diversity in early monumental design. Each site reflects its own blend of environmental conditions, community practices, and inherited knowledge. Another element that supports the idea of solstice alignments at Karahan-Tepe is the timing of its construction. The site predates settled agricultural villages in many parts of Southwest Asia. This means its builders were mobile hunter-gatherers or semi-sedentary groups, not farmers tracking planting seasons. If they cared about the solstice, it was not for agricultural timing. Instead, the solstice may have served as a navigational anchor, helping communities understand when certain migrations began or when particular resources became available. Seasonal changes in animal behaviour, plant growth and climatic conditions would have made the solstice a practical tool for planning movement and gathering. If the alignments at Karahan-Tepe indeed point to midwinter light, they reflect an ecological form of timekeeping that predates farming but is equally attuned to the cycles of survival. To build such alignments required a form of measurement that was observational rather than mathematical. People living in the early Holocene had generations of familiarity with the sky, watching the sun rise over the same plateau edges year after year. Small deviations in its position would have been noticeable to observers who relied on the land as their primary orientation system. The builders could have used simple techniques, tracking shadow lengths, marking horizon points with stones, or returning to the same vantage point each season. Through repeated observation, they could identify the point where the sun reached its lowest annual rise. When they finally built stone enclosures, this knowledge was already deeply embedded in their understanding of the world. Karahan-Tepe thus represents a transitional moment in human history. It shows that the impulse to shape architecture around the movements of the sky emerged independently of farming, literacy, and metalwork. It reveals that monumental design was not born from surplus or sedentary life, but from a worldview in which the sky served as a guide long before it became a symbol. In this sense, the solstice was a shared reference point across communities who otherwise lived highly mobile lives. The plateau became a stage upon which light and stone interacted each year, teaching observers when darkness had reached its peak and when light would return. When we place Karahan-Tepe in the wider timeline of early architecture, it becomes clear that the builders were not simply carving stones. They were carving time itself. The enclosures held the sun steady at its most fragile moment, transforming the winter solstice into a visible threshold in the landscape. The builders did not yet sow fields, but they sowed memory into stone. These alignments reveal that even before farming reshaped human life, people shaped the sky into architecture that carried meaning beyond utility. With architecture emerging, the meaning of light and shadow deepened. There is also the quiet question of how communities without long-term storage systems or rigid seasonal occupations came to treat certain shafts of light as meaningful enough to carve stone for. We do not know for certain, but evidence from nearby upland sites suggests a rhythm of movement that repeatedly returned people to the same natural terraces each year. In such places, the continuity of the landscape may have acted as the first instructor, teaching that the low winter sun always reappeared along the same path, sliding toward a single shallow notch before beginning its slow return. Over many generations, the memory of this horizon could have become inseparable from the memory of the place itself, encouraging groups to mark what the environment already displayed. At Karahan-Tepe, the plateau's line of eastern hills is particularly even, forming a broad, stable frame against which the midwinter sunrise would change very slowly, making the shift detectable even without permanent settlement. The carved pillars also raise a separate line of evidence about human attention. Many show subtle variations in girth and surface wear that indicate they were shaped at different times. implying the enclosure was not a single project, but rather a gradual accumulation of work. This incremental building pattern matches what archaeologists describe at comparable early Neolithic sanctuaries, where structures served as long-term gathering points, modified and reinterpreted as the community changed. In this reading, the solstice alignment would not have been a fixed or final achievement, but an orientation renewed by each generation's slight adjustments to the stone architecture. It may be that the builders were not trying to create a perfect solar calendar so much as reaffirm an inherited understanding of the sky each time they reshaped the pillars. One detail often overlooked is the floor itself. Excavations show carefully prepared surfaces, smoothed in some areas and left rough in others, as though different patches were meant to reflect or absorb light in distinct ways. Experiments at similar enclosures indicate that even slight variations in floor texture can influence how light pools or disperses during low sun angles. It is possible that people used these subtle visual cues to confirm that the shortest day had arrived, watching the contrast between shadow and stone change across the ground. Such practices require no numerical counting or written memory, only a persistent willingness to observe how winter sunlight behaves when it's at its weakest. As each new group returned to the plateau, the architecture may have served as a physical reminder that the sky could be interpreted. People living without written systems compensated through shared memory, and stone was one of the only mediums capable of holding those memories reliably. Even if the community shifted or dispersed, the pillars endured, preserving the orientation until someone returned to witness the same sliver of winter light finding its way between them again. In this sense, Karahantepe stands not only as an early monument, but as an experiment in how to stabilize the relationship between human perception and the celestial cycle. With architecture emerging, the meaning of light and shadow deepened. Imagine standing in an open clearing where the cold midwinter sun sits low enough that every object stretches its shadow far beyond its size, turning even a simple stone into a quiet instrument. Long before numbers, long before symbols were standardized, early builders learned that the sun could be read not by its shape or its brilliance, but by the darkness it cast. For people living without mechanical tools or written calendars, the changing length of a shadow was the most accessible way to sense the year's unfolding. A star might be too distant to measure, but a shadow could be touched, traced, and returned to day after day. This is why some of the earliest intentional markings on Earth do not point upward but outward along the ground. Archaeologists studying prehistoric landscapes have found isolated stones set upright in positions where their shadows stretch across stable surfaces during midwinter afternoons. We do not know for certain whether these stones functioned exactly as later gnomons would, but their placement suggests an awareness that shadow behaviour could reveal something consistent about the sun's motion. At a number of open-air sites, the ground around such stones shows repeated smoothing, as though people had tracked the shadow lengths across the same patch year after year. In some cases, shallow grooves worn into sunlit bedrock align with the extreme positions of midwinter shadow tips, marking a kind of seasonal boundary visible only during the shortest days. Evidence from field experiments across comparable terrains demonstrates that a community observing a single standing stone could have mapped the approach of the solstice with surprising accuracy simply by watching how its shadow elongated each afternoon. These shadow patterns mattered in ways that reached beyond a single day. On some prehistoric surfaces, faint divisions appear where lines were repeatedly incised or rubbed, perhaps indicating that people noticed how the shadow lengthened in predictable intervals as winter approached. Each interval would have given early groups a measurable fragment of the year, a way to anticipate returning scarcity or coordinate gatherings before deep cold settled. Ethnographic parallels from regions where horizon-based shadow watching persists show that such techniques require no specialized knowledge beyond repeated attention. Hunters in subarctic zones, for example, have used the angle of evening shadows cast by ridgetop stones to anticipate the return of migratory herds. Even without agriculture, these consistent visual cues shape decisions about movement, storage, and shelter. The link between shadow extremes and architecture also appears in early design choices at several prehistoric enclosures. Studies comparing these structures reveal that some walls or posts were positioned so that shadows reach specific interior points only around midwinter. Rather than illuminating chambers directly, the sun's indirect geometry was used to mark a transition in the season. These architectural features mirror what researchers have documented in later societies. That shadow behavior, not the stars alone, provided the earliest quantifiable system for marking time. Shadow was available to anyone. It required no elevated viewpoint, no clear night sky, no precise horizon knowledge. It simply asked people to watch how light failed, how darkness changed shape, and how both spoke of the sun's slow return. In this way, shadow became the first measurable language between humans and the sky. It gave form to an otherwise intangible cycle, and allowed communities to anticipate winters that came with little margin for error. By following the movement of their own silhouettes, or the stretching lines cast by stone markers, early humans found a method to divide the year without abstraction. They learned to read the absence of light as clearly as they once read the behaviour of animals or winds, and as each generation repeated these observations, the ground itself became a kind of memory, holding the long traces of sunlight in the patterns left behind. There is also the quieter matter of how shadows became trustworthy when so much else in early human life remained unpredictable. Winter storms could erase tracks overnight, rivers froze without warning, and the movement of animals shifted from year to year. But a shadow, cast from the same stone against the same patch of ground, returned each afternoon with a kind of patient consistency. It offered something no migrating herd or shifting weather pattern could offer, a rhythm that did not lie. We do not know for certain how long it took for groups to understand the value of this stability, but archaeological layers showing repeated use of flat rock surfaces near upright stones suggest a sustained commitment to watching. In places where the ground was scratched or worn smooth by centuries of observation, shadow became less an incidental effect of light and more a dependable instrument. At several prehistoric sites, archaeologists have documented shallow depressions positioned in front of standing stones that appear to have been intentionally prepared. These depressions often hold lighter-coloured sediment, as though people repeatedly cleared them of debris to expose the underlying stone. When researchers recreated midwinter conditions at similar locations, they found that these cleared patches created a more distinct contrast between the shadow's tip and the illuminated ground, making it easier to observe the approach to the solstice. This suggests that even without formal engineering, early observers adjusted their environment to improve the clarity of what they were watching. It was an early form of optimization, a simple refinement that turned natural behavior into a measurable pattern. What is particularly striking is that shadow-based timekeeping allowed communities to share knowledge without requiring permanent residence or controlled structures. A group passing through a familiar location could interpret the season instantly by examining where the afternoon shadow fell relative to known markers. This kind of situational awareness mattered for mobile societies living within landscapes that demanded flexibility. Shadow thus functioned not only as a temporal guide, but also as a communal reference point, making it possible for dispersed groups to maintain a shared understanding of the year even when they separated for long periods. Some of the earliest forms of spatial organisation may have grown from this practice. When architects of later periods drew on geometric principles to lay out enclosures or ceremonial spaces, they inherited a conception of order that had begun not with measurement tools, but with the observation of natural lines on the ground. Shadow taught the first lessons in proportion, symmetry, and direction, encouraging people to think about the relationship between vertical forms and the paths traced across the earth. This mental shift towards structured spatial thinking may have been one of the quiet catalysts that eventually allowed for the development of later megalithic projects, where geometry was no longer incidental but intentional. In the end, the significance of shadow lies not only in its practicality, but in the way it bridged the divide between the tangible and the celestial. Stone and sunlight met each afternoon at an angle that could be learned, remembered, and passed on. Through this meeting, early communities created the earliest shared language of time, long before stars were charted or seasons were written down. By responding to the subtle changes in darkness, people forged a relationship with the winter sun that would shape entire landscapes in the millennia ahead. Imagine watching people who have no written symbols, no recorded numbers, and no architectural plans begin to shape the land with a precision that seems far beyond the tools they carry. Picture a world in which the only fixed reference point arrives once a year, rising in the same place after the deepest night, giving early builders a single dependable moment from which to measure their surroundings. In such a world, geometry did not begin as abstraction. It began as a response to the winter sun returning exactly where it had been before. For communities without script, the midwinter sunrise became the closest thing to an absolute truth. Its position did not drift from memory the way stories could. It did not change shape like the patterns of weather. It returned year after year, offering a stable anchor that even the most mobile societies could trust. Archaeologists studying early megalithic Europe have observed that many of the oldest structures share a subtle but consistent orientation linked to this returning sun. The axis created by the winter solstice sunrise and the direction opposite it created a natural frame for builders, allowing them to align structures without mathematics, compasses, or written measurements. The midwinter sun provided the first cardinal point that mattered, and from it early communities could infer a sense of direction. Once this axial orientation was understood, symmetry became easier to imagine. Even the earliest enclosed structures show an attempt to balance the spacing of stones across a central line, a pattern that emerges repeatedly in Neolithic Britain. Excavations reveal that builders place stones in pairs or opposing positions, not by applying numerical ratios but by replicating distance visually, using the returning sun as their guide for orientation. In the landscapes of Britain, the rise of symmetry coincides with increasing architectural standardization. When we look at multiple stone circles built several centuries apart, we notice that their shapes become gradually more regular over time. At first, the outer rings appear slightly uneven, as though the builders were learning through trial and error. But across generations, the circles achieve a clearer proportion, suggesting a transfer of knowledge. Archaeologists do not yet know whether this knowledge was communicated verbally, through demonstration, or simply through repeated building, but the improvement is visible in the archaeology itself. Structures built in the later 4th millennium BCE show tighter spacing of stones, more consistent diameters, and more deliberate alignments than those erected centuries earlier. Repetitive geometrical patterns appear in these settings as well. Some stone circles adopt alternating stone sizes, creating a purposeful rhythm in their layout. Others use repeated distances between stones, forming polygonal shapes with astonishing regularity for communities without recorded measurements. Even in timber circles predating stone monuments, archaeologists have discovered trench lines and post-hole arrangements that reveal half-formed geometrical concepts. These patterns suggest that geometry emerged not as a single invention, but as a cumulative feature of early architectural practice. Each generation refined the work of the one before, learning not from diagrams but from the stones themselves. Perhaps the most compelling insight comes from archaeological evidence demonstrating that early builders often corrected or rebuilt sections of monuments over time. In some circles, earlier stones were removed and repositioned, creating more precise symmetry or alignment. This shows that the builders were not simply following tradition blindly. They were evaluating, adjusting, and refining, using the structure as a living blueprint. The monument became both the instruction and the result. Through this process of building, observing, and rebuilding, geometry developed as a material practice rather than an intellectual theory. This slow emergence of geometric thought is made even more remarkable by how reliably it corresponds to the solstice cycle. The midwinter sun was the fixed point from which all variation was measured. It was the most dependable moment of the year, and by anchoring architecture to it, early communities created spatial systems that endured. Out of this return came a sense of proportion. Out of proportion came symmetry. And from symmetry, the earliest forms of geometry began to unfold. It is a reminder that mathematical thinking did not begin in the mind alone. It began on the ground beneath the low winter sun, where shadows and stone taught the first lessons in order. The next step was permanence. There is something quietly revealing in the way these early structures show imperfections, because the imperfections record the moment when geometry was still being discovered rather than enforced. At several Neolithic sites, archaeologists have uncovered small test pits dug beside larger monuments, as though builders practiced setting posts or stones at the correct spacing before committing to the main circle. These pits often contained fragments of broken tools and compacted footprints, suggesting repeated human traffic in confined areas. It may be that these were early training grounds, places where younger members of the community learned how to judge distance not by counting, but by pacing, by stretching rope, or by aligning the human body against the returning sun. Such preparatory spaces allow us to glimpse the earlier stages of architectural learning, long before plans existed on any physical medium. Some monuments show another kind of experiment: gradual expansion. A circular structure might begin with a modest ring, only to develop a larger outer ring several decades later. This pattern of enlargement suggests that once a community achieved a certain geometric confidence, they scaled up their ambitions. Enlarging a circle would have required re-evaluating the central axis, repositioning stones, and recalculating spacing through embodied methods. Archaeologists studying these expansions note that the outer rings often show greater regularity than the inner ones, strengthening the interpretation that geometry matured through construction itself. The landscape, in a sense, became the classroom, and every monument was part of the curriculum. In regions where stone was not readily available, such as parts of Central Europe, geometry was expressed through earthworks. Ditches and banks carved into the soil reveal careful attention to proportion, with entrances placed at specific intervals and embankments shaped to define symmetrical spaces. These earthworks demonstrate that geometric thinking was not limited to megalithic cultures alone, nor was it dependent on monumental scale. Even modest structures reflect decisions about alignment, proportion, and balance, decisions guided by the sun's fixed return rather than numerical systems. One particularly striking example comes from a series of causewayed enclosures. where archaeologists have found evidence that entrances were positioned to align with specific solar events. But beyond these alignments, the internal divisions of the enclosures reveal a geometric logic in the placement of pits and fences. Measurements show that the spacing between features often follows a consistent pattern, replicated even when the structures were rebuilt. This suggests a communal agreement on spatial organisation, transmitted through shared observation rather than explicit measurement. The solstice did not simply inspire direction, it inspired order. What makes this development so remarkable is that geometry here is inseparable from human movement. Without written records, early builders relied on their bodies as instruments. A measured pace, a stretched arm, a rope pulled taut between two stakes. These were the units from which space was composed. The solstice provided the orientation, and the body provided the scale. Together they created the earliest system by which humans could transform open land into coherent shape. This embodied geometry would persist in many cultures for millennia, becoming embedded in traditions of pacing, rope stretching and horizon marking long before mathematical treatises emerged. The archaeological record also shows hints that these early designs became tied to social identity. Communities that returned to a monument year after year not only recognized the geometry of the structure, they internalized it. The way stones curved, the way entrances framed the sun, and the way paths wound between posts became part of collective memory. Geometry thus became not just an intellectual framework, but a cultural one, shaping how people imagined their world and their place within it. The concept of symmetry may have mirrored a deeper desire for stability and continuity at a time when much of life was shaped by uncertainty. In the quiet precision of these monuments, we can sense this emerging relationship between human intention and celestial rhythm. Geometry did not arrive as a discovery written down by a single thinker. It arrived slowly, woven into the daily return of light, refined through practice, and anchored each year by a sunrise that could be depended upon. Through this process, early humans moved from observing the world to shaping it with purpose, creating structures that echoed the reliable geometry of the sky. The next step was permanence. Imagine entering a structure so precisely shaped that the entire year narrows into a single beam of sunlight, a beam that appears only once every winter and touches the innermost stones as though the monument were waiting for it. Picture a chamber buried beneath a grassy mound, sealed from wind and noise, where the cold midwinter sun climbs low across the horizon and sends one thin line of light into the dark. For the people who built Newgrange more than 5,000 years ago, this moment was not a metaphor or a myth. It was a calculation brought into being through stone. The winter solstice, which earlier societies watched from the open landscape, became something they could walk inside. They shaped the year itself into architecture. Archaeologists studying Newgrange have long noted that the roof box above its entrance is not decorative. Its angled stones form a controlled aperture that admits sunlight only when the midwinter sun rises at its lowest arc. We do not know for certain whether the builders tested multiple positions or began with a full understanding of the solar path, but the final arrangement shows an understanding that cannot be accidental. The roof box lifts the rising sun above the external ground level, directing it deeper than the entrance passage alone could allow. When the alignment succeeds, the beam travels along the corridor for several minutes, illuminating the chamber's interior basin, the carved stones behind it, and the curve of the roof. For a brief period during the solstice window, the entire monument becomes an instrument designed to receive the returning sun. The orientation of the passage is even more deliberate. While many megalithic structures in Europe are broadly aligned to cardinal directions or to solar events, Newgrange's passage is angled to match a very narrow slice of the horizon. Studies show that only the sunrises close to the winter solstice enter the chamber in this way. If the builders had deviated even slightly in the pitch or angle of the passage, the light would fail to reach the central basin. Excavations reveal that later generations repaired and maintained the mound, suggesting that its solar function mattered long after the initial construction. This continuity implies that the solstice alignment was not incidental. It was part of the monument's purpose. The quartz stone facade adds another layer of insight. When the structure was restored, archaeologists identified large quantities of white quartz that originally formed a bright reflecting surface at the entrance. In winter sunlight, this quartz would have intensified the glow cast into the roof box and passage, amplifying the contrast between darkness and light. It also would have made the monument visible from a distance, transforming the mound into a seasonal beacon. The facade's reflective quality indicates that people understood how materials interact with light and chose specific stones to shape the visual impact of the solstice event. Excavation layers inside the mound show long-term use. Charcoal remnants, pottery fragments, and traces of human presence suggest that communities returned to Newgrange repeatedly over centuries. Some layers indicate ritual fires, others reflect maintenance activity, and still others hint at gatherings timed around the solstice. These layers remind us that the monument was not a static symbol. It was an evolving site of memory and observation. Each generation left its mark in the chambers, in the floor deposits, and in the wear patterns on the carved stones. The internal acoustics of Newgrange reveal something else about its design. Researchers conducting experiments inside the chamber found that the corbelled roof creates a resonance at specific frequencies. When voices or instruments reach those frequencies, the chamber amplifies the sound. It is possible that the builders understood this property through repeated use rather than calculation, but the effect is striking. The solstice beam does not simply light the space. It enters a room that responds to human sound in an unusual way, making the experience of the returning sun both visual and auditory. The chamber becomes a place where light and sound converge, creating an atmosphere that is part engineering, part environmental awareness. In this combination of alignment, material choice, acoustic sensitivity and long-term use, we can see how Newgrange turned the year into a physical journey. To walk into the passage on the solstice was to walk into time itself, to move from the darkness of the mound to the brief return of light in a way that mirrored the turning of the year outside. The sun became a measurable visitor, not a distant symbol or a passing effect. It entered the monument on schedule, confirming the careful work of the builders and reminding the community that their world remained in rhythm. There is another detail inside Newgrange that often goes unnoticed until it is experienced in person. The way the chamber's stone surfaces seem to guide the light as it moves. The carved spirals, arcs and parallel lines etched into the curbstones and interior slabs are arranged so that the solstice beam brushes across them in sequence. The carvings are not illuminated all at once. Instead, the light advances slowly along one motif before reaching another, as though the walls themselves were marking the passage of those minutes. Archaeologists debate the exact meaning of the motifs, but their placement relative to the solstice beam is too precise to be accidental. The carvings become visible only when the sun enters the passage at the correct angle. For the rest of the year, they sit in near total darkness. This suggests that the chamber was designed not only to receive sunlight, but to reveal parts of itself only when the year reached its turning point. The duration of illumination inside Newgrange is also instructive. Modern reconstructions show that the beam remains visible inside the chamber for a short interval before sunrise reaches its peak. This interval is long enough for people to gather, observe, and possibly conduct activities that required coordination, yet short enough to retain rarity. The window of alignment spans only a handful of days each year, creating a period of anticipation followed by a sudden, unmistakable confirmation that the year has begun to shift. It was a calendar the body could experience, first the cold, then the light, then the fading of the beam as the sun rose beyond the roof box's reach. Outside the mound, the surrounding landscape reinforces this sense of timing. Studies of the Boyne Valley indicate that the nearby river floods seasonally, changing its reflective surface around midwinter. During this period, the river acts as a broad mirror, enhancing the brightness of sunrise along the valley. While we cannot know whether the builders positioned Newgrange with full knowledge of this seasonal reflection, the alignment between the chamber's orientation and the valley's natural shape suggests an awareness of how land and light interact. The monument stands not in isolation, but as part of a wider environmental choreography in which water, horizon and sun work together. Excavations also reveal that Newgrange was part of a larger network of related monuments. Not far from it stand Noath and Dowth, structures that share architectural similarities but differ in alignment. Noath, for example, has passages oriented toward the equinoxes rather than the solstice. This distribution of solar orientations implies a broader understanding of the year, with different sites marking different thresholds. By situating Newgrange within this network, early communities created a landscape where time was not measured by a single monument, but by a system of them. People could move through the valley and encounter different phases of the year embodied in stone. The long-term use of Newgrange further strengthens the idea that it functioned as a calendar rather than as a static tomb or isolated ritual chamber. Some layers show evidence of periodic refurbishment, including the resetting of stones and the addition of new materials to the mound. These repairs suggest that communities maintain the structure to ensure its continued alignment with the solstice. They were not simply preserving a monument, they were preserving its function. The alignment needed to remain precise, and that precision required attention across generations. What emerges from all of this is a picture of early engineering deeply tied to observational patience. The people who built Newgrange were not working from diagrams or formal theory. They were working from the sky. They studied how light entered space, how stone held shape, how the year could be tracked through a single moment, and how a community could return to that moment again and again without losing its meaning. The passage, the roof box, the carvings, the acoustic chamber, and the mound together formed a system that transformed the winter solstice into an event that could be experienced with the senses. It was the first year made tangible, the first calendar that people could step inside rather than read. Yet Newgrange was only one part of a wider shift. Imagine walking across a landscape where every pathway, every ditch, every ring of timber and stone seems to point toward the same moment in the year. Picture rising ground that appears ordinary at first, until you realize its avenues curve toward a single sunset, and its gathering spaces fill only when the days are shortest. In such a place, the solstice becomes more than an astronomical event. It becomes the thread that binds an entire region. This is what archaeologists see in the plain surrounding Stonehenge, a place where alignment was not confined to a monument, but was woven into the land itself. The most visible clue lies in the Stonehenge Avenue, a long deliberate corridor of banks and ditches extending from the monument toward the River Avon. When researchers mapped its orientation, they discovered that it frames the midwinter sunset with remarkable accuracy. We do not know for certain whether this orientation was chosen at the earlier stage of construction or refined over generations, but the avenue's final form shows a clear intention. to guide people toward the setting sun on the shortest day. Standing along the avenue at dusk, the sun drops directly into its axis, turning the corridor into a processional route defined by light. Beyond Stonehenge itself lies Durrington Walls, a vast settlement site occupied seasonally rather than permanently. Excavations show that its peak activity occurred during the cold months, when hundreds, possibly thousands of people gathered to feast near the winter solstice. The settlement's southern circle, built of massive timber posts, is oriented toward the midwinter sunrise. This creates a striking complement to Stonehenge's orientation: a sunrise at one place, a sunset at the other. The landscape becomes a cycle. Research suggests that people may have moved between these sites, witnessing dawn at one and dusk at the other during the solstice period. The bluestones at Stonehenge add an additional layer of insight. Quarried from Wales and transported over great distances, they were placed in patterns that changed across centuries. Some arrangements form arcs that mirror the solstitial axis, while others reinforce the monument's bilateral symmetry. These stones appear to have been repositioned multiple times, suggesting that their placement was part of an ongoing experiment in how best to anchor the monument to celestial events. Such reconfiguration implies a continuous engagement with the solstice, not a single moment of construction frozen in time. Seasonal feasting remains at Durrington Walls provide further evidence that the winter solstice shaped not only architecture but social rhythm. Bones from pigs and cattle show butchering patterns consistent with animals slaughtered at the peak of winter. Cut marks and age profiles match seasonal husbandry cycles, indicating that herds were managed specifically with midwinter gatherings in mind. When combined with pottery deposits, hearths, and the layout of the houses, the picture that emerges is one of coordinated return, people travelling across the region to converge at the moment when daylight reached its minimum. The coherence of alignments across multiple structures reinforces the idea that this was not a scattered set of practices, but a region-wide orientation. When archaeologists map the azimuths of Stonehenge, Woodhenge, the Cursus and related sites, they see patterns that repeat with deliberate variation. Each structure participates in a broader choreography. It is as if the builders treated the solstice not just as a point on the horizon, but as an organising principle for how space should be shaped. The sun's path gave the region its structure, and human activity followed that structure with remarkable consistency. Taken together, these elements reveal that the solstice had become an anchor of unprecedented scale. It guided the layout of ceremonial avenues, shaped seasonal migration patterns, influenced livestock management, and infused architectural decisions with shared meaning. Communities living far from the monument itself recognized the same celestial event, creating a unified landscape of observance. Stonehenge was not merely a place to watch the solstice, it was the centre of a land designed to express it. This shift marks a turning point in human history, the moment when celestial observation became woven into the geography of daily life, when light itself began to command the shape of the land. Another layer of this landscape becomes visible when archaeologists examine the subtle earthworks that extend far beyond Stonehenge's immediate surroundings. Across Salisbury Plain lie dozens of lesser-known monuments whose orientations echo the same celestial logic. Some are modest rings of post holes, others elongated mounds, and others still are causewayed features that barely rise above the grass. What connects them is not their shape, but the way their openings or long axes respond to the winter sun. These features, scattered across kilometres of terrain, form a silent constellation on the ground, each one pointing toward the same turning of the year. We do not know for certain whether these alignments were coordinated by a central authority, or emerge through shared cultural memory, but their consistency suggests a common way of reading the sky. Recent geophysical surveys have revealed additional structures that deepen this picture. Beneath fields that now appear empty, buried ditches and ringed enclosures show orientations nearly identical to those of Stonehenge and Durrington walls. Some of these features never held stones at all. They existed as negative space carved into the earth to mark a moment rather than host a gathering. This approach to monumental design, creating meaning through absence rather than presence, adds a quiet sophistication to the region's architectural language. It suggests that the solstice was not tied to a single type of monument. Instead, it permeated the entire landscape, guiding construction at multiple scales. The coordination between sites becomes clearer when archaeologists investigate movement across the plain. Pathways worn into chalk soils, preserved only in patches, show repeated seasonal use leading towards Stonehenge from various directions. These paths converge like tributaries, suggesting that midwinter journeys were not spontaneous gatherings, but anticipated migrations woven into annual cycles. The presence of discarded tools, broken pottery and food debris along these routes indicates brief halts, perhaps rest points or places where people pause to prepare offerings before entering the ceremonial core of the landscape. One of the most revealing discoveries comes from isotopic analysis of animal bones found at Durrington walls. These studies show that many animals brought to the site were raised far from Salisbury Plain. Their chemical signatures match regions in Western Britain and even parts of Scotland. This tells us that the midwinter gathering drew people and livestock from distant communities. The solstice alignment of the region was not simply a local phenomenon. It was a magnet that pulled people across long distances, creating a seasonal network that extended far beyond any single settlement. There's also evidence that some of the region's monuments changed orientation over time. At certain sites, later constructions overlay earlier ones with slightly altered azimuths, as if the builders refined their understanding of the solstice, or wished to emphasize a different phase of the sun's journey. These adjustments imply that the meaning of the solstice was dynamic, evolving as knowledge and cultural priorities shifted. The landscape in this sense was not fixed. It was a living document, revised with each generation's interpretation of the sky. The materials used in Stonehenge's construction add another dimension to this landscape-wide alignment. Some stones appear to have been chosen not for their size but for their acoustic properties, producing resonant tones when struck. Experiments with these sonic stones suggest that sound may have played a role in midwinter gatherings, reinforcing the sensory experience of the solstice event. The alignment, therefore, was not purely visual. It may have been part of a multi-sensory environment shaped by sound, movement, and light. Across all of these findings lies a deeper truth. The solstice provided the first shared horizon for communities separated by distance and language. It was a stable point that did not belong to any one group yet could be recognized by all. By aligning monuments to this point, early societies created a landscape where time itself was communal. When people walked towards Stonehenge or Durrington walls at midwinter, they were not merely joining a celebration. They were participating in a regional ritual of orientation, placing themselves within a broader system that linked earth, sky, and movement. Far away, a very different environment produced the same outcome. Imagine standing in a desert where the land is so open, so stripped of shelter and shadow, that the winter sun seems impossible to measure. There is no forest edge, no tall stone, no cave mouth narrowing the light. There is only sky and horizon in every direction. And yet in such places ancient societies found ways to follow the darkest day of the year, with more subtlety than many forest cultures ever achieved. The paradox is simple. The fewer the features, the sharper the eye must become. The desert demands a different kind of astronomy. It forces attention not to one object, but to the relationship between light and landscape stretched across vast space. So picture a world where the horizon itself becomes the instrument, and the human eye becomes the moving part. What if I told you that long before European stone circles, long before monumental passage tombs or timber alignments, desert peoples across the American Southwest created a network of observatories where the solstice could be read from nothing more than the passing of a shadow across a cliff face? We do not know how early this knowledge emerged, but by the first millennium of the Common Era, the region around Chaco Canyon had developed a landscape-scale architecture that allowed entire communities to track the winter sun with astonishing precision. The revelation is clear. Where the environment offered no natural shade, they learned to measure the year through the exact movement of sunlight on stone. The evidence begins with Fajada Butte, a lone tower of sandstone rising from the desert floor. Near its summit, 3 rock slabs lean against the cliff in a configuration that appears accidental at first glance. But when researchers documented the sun's movement across these panels, they saw something extraordinary. At the winter solstice, a thin beam of light passes between the slabs and strikes a spiral petroglyph carved on the cliff face. On other days, the beam misses. On the solstice, it cleaves the spiral precisely. This sun dagger, as it is called, is not a symbol. It is a measurement. And it works not because the slabs were placed randomly, but because their arrangement allows sunlight to shift gradually across the carved spiral until the exact moment of midwinter is reached. We do not know for certain whether the slabs were intentionally positioned, but the consistency of the effect, the skill of the carving, and the broader Chaco tradition of astronomical alignment make coincidence extremely unlikely. The desert itself became the instrument, and the solstice became the calibration point. In nearby regions, similar relationships between architecture and winter light emerge. At Cliff Palace in Mesa Verde, the great sandstone alcove shelters a cluster of towers and ceremonial structures whose orientations hint at seasonal awareness. Light enters the alcove at sharply different angles during the solstice period, illuminating specific niches only during midwinter. The timing aligns with evidence of seasonal occupation, suggesting that communities gathered here when the sun reached its lowest arc. The architecture did not force the sunlight, it simply waited for the moment when the sun could reach it. And in that waiting, a relationship between place and season emerged, quiet and deliberate. Further across the region, petroglyphs carved into cliff faces show repeated patterns associated with seasonal sunlight. Some spirals darken at equinox, others brighten at winter, depending on the cliff's angle and the rock's weathering. Geologists studying these sites note that the surfaces chosen are particularly stable, meaning their interaction with sunlight has remained unchanged across centuries. The petroglyphs function as reference marks, carved on surfaces that do not shift or erode rapidly. They transform a cliff into a calendar, one that is impossible to move and therefore impossible to misinterpret. They also standardize time across communities. A winter mark carved on one cliff can correspond to a light effect on another canyon wall many kilometers away. This coherence allowed dispersed settlements to recognize the same moment. Throughout the Chaco world, the canyon walls themselves became shadow catchers. Their vertical planes offered a contrast grid where the smallest movement of sunlight could be read accurately. Archaeologists have mapped shadow lines that move predictably across these surfaces throughout the year. When the sun hangs low in midwinter, these lines reach their minimum length, offering another way to recognize the solstice. The method is subtle, almost invisible unless one knows where to look. But it requires no tools, no specialized structures, no high vantage point. It requires only sky and stone and the memory of where light last touched. The broader region reveals networks of sites, aligned not by roads or walls, but by timing. Chaco great houses appear to have coordinated their seasonal activities across distances that stretch for hundreds of kilometers. Radiocarbon data from seasonal middens suggests that gatherings concentrated around midwinter. Signal fires or long-distance line-of-sight communication may have allowed communities to participate in the same solstice observance. But the common thread is simple. The winter sun provided the schedule. The desert enforced its terms, and people learned to follow them. Realization arrives quietly here, as it often does when the environment shapes behavior rather than belief. Even in barren landscapes with no built monuments to catch the sun, the solstice left a signature carved in light. It is a reminder that the oldest calendars are not necessarily the most monumental. Sometimes the largest observatory is an entire horizon, and the most faithful instrument is a cliff face that has not moved for thousands of years. There is another detail, often overlooked, that shows how quietly sophisticated this desert astronomy became. In many canyons of the southwest, especially those bordering Chaconne road systems, archaeologists have found small, shallow peck depressions carved into ledges that receive winter sunlight at specific hours. These depressions are not symbolic in appearance, they are functional. When the sun is low enough, the light enters at an angle that fills the depression entirely, creating a bright disk against the darker sandstone. Throughout the year, the depth of shadow inside these cups shifts in predictable cycles. When the cup fills perfectly, midwinter is near. When the disk breaks into two, or when shadows bisect it diagonally, the solstice has passed. This form of measurement is almost unbelievably minimalistic. It turns the sun into a slowly advancing liquid that pours into a carved cavity, marking time without words or instruments. Another line of evidence comes from dendrochronology, the study of tree ring sequences recovered from ancient beams at Chaco great houses. These timbers were cut at specific times of year, and a surprising number cluster around the winter months. We do not know if this reflects ritual preference, logistical convenience, or climatic advantage, but the pattern indicates that winter was not a dormant season. It was a moment of intention, when labour mobilised across the region to prepare or repair monumental structures. The consistency implies that people knew precisely when winter began, and that this knowledge shaped the scheduling of communal construction. The solstice, in other words, was not only observed, it directed work. In some canyons, archaeologists have documented rock alignments that are so subtle they were never recognised until satellite imagery became available. Lines of scattered boulders, positioned with surprising regularity, correspond to sightlines extending from one cliff outcrop to another. When projected across the landscape, these alignments intersect with petroglyph panels that record critical solar events. The system functions almost like a vast open-air corridor through which the winter sun travels across multiple days. Humans moving along this corridor could read the sun's progress by noting which boulder cast which shadow upon an opposing wall. These alignments suggest coordination beyond the scale of a single settlement. They imply a shared knowledge system extending across communities, all tied to the slow descent of the winter sun. Even the acoustics of certain alcoves contribute to this seasonal architecture. Researchers studying the sound properties of Mesa Verde and related cliff dwellings have noted that some chambers amplify low-frequency vocalizations during the winter months, when humidity and air density change. This shift is small, yet noticeable. It means that the experience of gathering in these alcoves would subtly transform around midwinter, reinforcing a sensory cue that the darker season had begun. In a world without calendars or clocks, atmospheres communicate. The solstice is not only seen, it is heard in the way sound moves differently through cold air over stone. In regional networks where long-distance signalling mattered, archaeologists have also identified mesotopes with wide visibility, some of which align closely with winter sunrise or sunset angles. A fire lit on one of these high points at solstice would have been visible across tens of kilometres. If multiple high points relayed the signal, entire regions could synchronise their gatherings or ceremonies. Whether or not such signalling was formalised, the repeated placement of structures on these elevated sites suggests intentionality rooted in horizon awareness. The horizon is never neutral in the desert. It is a ledger of time. All of this converges into a simple realization. When people live long enough within a landscape that exposes every movement of the sun, the land becomes inseparable from the calendar. No markers need to be carried. No monuments need to be built. The desert itself is the device. And by learning how to read its signatures, people transformed the vastness around them into a slow, precise instrument of timekeeping. In such places, the solstice is not an event recorded, it is an event lived. It is the shifting of light on the skin, the thinning of the day's warmth, the angle of the sun slipping into a position it has not held in a year. Observing the solstice in the desert is not difficult. It is unavoidable, and that certainty shaped the rhythm of whole societies. But not all societies used stone. Some used mountains. Picture a moment when a small community wakes before dawn, not to greet the sun directly, but to watch a single peak on the far horizon. The people stand quietly, wrapped in hides or woven fibres, facing a silhouette that has not changed in their lifetime or in the lives of their ancestors. They know that when the sun rises at the mountain's left shoulder, winter has begun. When it rises at its right, the dark season is ending, and when it climbs directly above the centre point, spilling its first light over the ridge in a thin, precise line, the world has reached a hinge in the year. Imagine measuring time not with stone monuments, carved symbols or tools, but with the shape of the earth itself. What if I told you that long before humans raised circles of timber or aligned stones toward the solstice, they were already orienting their lives, settlements, and seasonal movements around the way sunlight interacts with mountains? The revelation is simple. The earlier solar monuments were not built by human hands. They existed already in the world, carved by tectonic pressure, wind erosion, glacial retreat, and deep geological time. And people learned to use these immovable forms as the first great calendars, long before agriculture, long before writing, and long before ritual became codified into myth. We do not know when the first community recognized that the winter sun rose at a slightly different point on the horizon each day. But we do know that mountains make this movement visible in a way few other landforms do. A peak offers a fixed silhouette. A notch in the ridge creates a natural frame. A sloping shoulder becomes a simple, reliable indicator of the sun's shifting path. In regions across Europe, East Asia and the Andean highlands, ethnographic and archaeological evidence suggests that horizon-based solstice tracking was not an isolated discovery. It emerged independently wherever mountains dominated the landscape. In the high plains of prehistoric Europe, for example, many Paleolithic sites sit at the edge of basins where a single distant peak marks the winter sunrise. Paleo-environmental reconstructions show that these basins were long-term habitation areas and that certain rock shelters face directly toward these natural horizon markers. These alignments are not precise in the way later architectures would be. They are looser, more observational than engineered, yet they reveal something crucial. people positioned their shelters where the mountain's seasonal shadows or sunrise lines would be visible. The landscape was not neutral. It was chosen for its ability to reveal time. Across the Andes, the relationship between mountain silhouettes and solstice tracking becomes even clearer. Ethnographers working with communities in the highlands have documented how notches, twin peaks, or abrupt ridgelines function as solar markers. When the sun touches the notch at midwinter, it signals the beginning of specific pastoral cycles. Llama and alpaca herding patterns shift. Agricultural plots are prepared or abandoned depending on which part of the mountain the sun touches first. Though these practices are modern, archaeological evidence from pre-Columbian settlements shows continuity in how ancient structures were oriented relative to horizon features. It suggests that the principle stretches back many centuries, possibly millennia. East Asian traditions provide another layer of evidence. In parts of prehistoric China and the Korean peninsula, early communities built seasonal dwellings with entrances oriented toward the horizon point, where the winter sun rises between two distant hills. Excavations show that these orientations remain consistent even as the architectural materials change from wattle and daub to more stabilized structures. The settlement rotates only when the location of the sunrise marker shifts behind a different peak, likely due to population movement rather than astronomical change. This implies that the people carried the idea with them. The solstice was something read from mountains, not from the sky alone. In many regions, seasonal migration routes follow the movement of mountain shadows. This may sound poetic, but it is grounded in ecology. At high altitudes, shadow length determines frost duration, which affects plant growth and the presence of certain grazing animals. Paleobotanical records from mountain valleys in Europe and Central Asia show cycles of vegetation that track closely with winter solar angles. Communities that move seasonally between high and low pastures would have learned to read these patterns intuitively. They walked with the sun, even if they did not understand its geometry. Mountain-based observation persists archaeologically through settlement patterns that cluster beneath specific peaks. These peaks are not necessarily the tallest or most imposing. They are the ones that provide reliable visual cues at dawn or dusk. In the Alps, for instance, Neolithic habitation sites repeatedly appear beneath ridgelines, whose silhouettes create sharp horizons. At these locations, the winter sunrise emerges predictably from the same notch every year. Paleo-environmental layers suggest long-term occupation, sometimes spanning thousands of years, which indicates that communities remain tied to the same visual anchor across many generations. The peak became a shared reference, a natural clock inherited rather than built. What is striking is how similar this pattern is across continents. In the Andes, peaks associated with solstice sunrise or sunset also correspond to ancient settlement clusters. In East Asia, villages align with visible mountain profiles. In Europe, rock shelters and open-air camps consistently face horizon markers that match seasonal solar angles. The convergence is not accidental. It points to a universal problem faced by early humans: how to know when the darkest day arrives, and how to know when its return has begun. Mountains solved that problem. They created a stable horizon index. When the sun moves behind or above a fixed silhouette, the event becomes legible, predictable, and shareable across a community. No monument can compete with the permanence of a mountain. No stone circle can match its scale. To use a peak as a calendar is to use deep time as a tool. The realization emerges slowly here, from evidence rather than mystery. Before humans carved symbols or raised megaliths, they learned to read the world. They learned that mountains do not lie. They do not shift in memory. They do not drift with seasons. and so the landscape itself became the earlier solar monument, a natural observatory older than any human design, older than agriculture, older than settled life. It suggests that our first calendars were not inventions, they were recognitions. There is another dimension to mountain-based timekeeping that becomes visible only when we examine the archaeology of movement. Many early communities did not remain in a single settlement throughout the year. They shifted locations following herds, ripening plants, or safer winter elevations. When these groups travelled, they often carried no portable markers of the season with them. Instead, they relied on the mountains themselves as the continuity that held meaning across distance. A single peak, visible from multiple valleys, becomes a stabilizing reference point. When the sun touches its southernmost limit along that peak, the year turns. In this sense, mountains became companions across movement, the only fixed presence in a life defined by mobility. We can see this in the archaeological record of the Carpathians, where seasonal sites appear in vertical sequences along the same mountain faces. Even when the campsites shift by hundreds of meters in elevation, the line of sunrise over the horizon remains aligned with a particular ridge. People changed position. The marker did not. Paleoclimate indicators taken from nearby peat cores show winter severity fluctuating dramatically during the early Holocene, yet the horizon remained stable as a guide. It is a reminder that the land carries its own memory even when human communities are forced to adapt. In the Andean region, additional evidence emerges through the orientation of agricultural terraces built in later periods, long after the earlier solstice watchers. Although these terraces belong to cultures far removed from the Paleolithic world, they often preserve even older horizon markers by aligning the upper terraces towards solstice notches in surrounding peaks. Soil studies show multiple construction phases layered atop one another, some stretching back more than 2,000 years. This continuity suggests that long before monumental ritual centres were constructed, farming communities already treated certain mountains as anchors in the agricultural cycle. The calendar was not written in stone, but inscribed in the direction of cultivation. Even in regions where mountains are distant rather than immediate, they still shape time. In parts of northern China, communities settled on plains where the nearest significant peak lay more than 50 kilometres away. Yet excavations reveal that house entrances and hearth orientations consistently face toward that distant horizon mark, aligning with the sunrise around midwinter. Such alignments require careful observation because the sun rises at a shallow angle near the solstice. Only someone watching for many years would notice that the sun touches the mountain's left edge before gradually climbing above the ridge. This patience reflects a culture trained to observe change at the slowest possible scale. What makes the mountainer's calendar so compelling is that it requires neither specialized instruments nor rare skills. It thrives on accessibility. A mountain is visible to everyone: elders, hunters, children, travelers, those at the center of the community and those on its margins. The solstice becomes a shared event not because of ceremony, but because of visibility. When the first rays of the midwinter sunlight reach a particular notch, the entire settlement can see it simultaneously. Time becomes communal rather than technical, felt rather than calculated. There is also a sensory quality to horizon watching that archaeological evidence can only gesture toward. Mountains amplify light. The sun's edge brightens differently when rising beside a granite peak than when emerging above open plains. Temperature shifts more sharply at dawn in valleys enclosed by ridges. Shadows lengthen at different speeds as they slide down steep faces. People who lived beneath mountains experienced these changes as part of their bodily rhythms long before they could name them. In this way, the solstice was not only observed visually, It was experienced as a physical event, colder air settling along slopes, wind patterns shifting direction, scents carried differently across rock formations. Across continents, mountains also created places where long-term observation became practical. A notch carved by glacial action does not move. A saddle between peaks remains constant across millennia. These stable features allow communities to accumulate generational knowledge. A child learns from an elder not through instruction, but by watching where the elder's eyes turn at dawn. When the sun reaches the same place decades later, the memory becomes embedded in the landscape. Archaeology rarely preserves such memories directly, but settlement continuity beneath the same horizon, markers for thousands of years, reveals their presence. The realization here is quieter than in earlier segments. It suggests that the first solar observatories required no architects and no monumental effort. They existed wherever people lived long enough to notice the world's rhythms. Mountains made the solstice legible. They turned the sky into a story the earth was already telling. From mountains came meaning. A community of late Neolithic people standing at the edge of another short winter day, each person aware not only of the cold on their skin, but of the precise rhythm with which the light has been shrinking for weeks. In earlier times, this shrinking felt like a threat. Now, in these more settled landscapes, something else begins to take shape. The people who gather beneath the quiet arc of the sun are no longer simply reacting to the darkening world. They're counting, they're remembering, and for the first time in human history they are beginning to understand that the sky is not merely changing, but changing in a way that could be anticipated. This is the threshold where observation becomes knowledge, where repetition becomes recognition, and where the seed of future mythology is first planted in an entirely scientific soil. Archaeologists studying late Neolithic layers across Europe and Western Asia have noted something subtle but important. Patterns of construction and settlement that reflect a new type of cognition. We do not know the names of the individuals who first recognized these skybound repetitions, but the evidence suggests that by roughly the 4th millennium before the Common Era, there were people whose attention to the solstice was not limited to a single event. Instead, they watched the same point on the horizon over many years, noting that the sunrise always returned there after the longest night, shifting slowly back and forth across a predictable corridor. Climatic records taken from lake sediments and peat cores show seasonal cycles becoming increasingly stable during certain Neolithic phases, offering a natural stability that made regularity noticeable to human observers. Predictability itself became a kind of revelation. Within several excavated settlements in Britain, Central Europe and the Near East, archaeologists have begun identifying signs that some members of these communities occupied roles with responsibilities distinct from farming, herding, or tool-making. These were not astronomers in a modern sense, but individuals who sat at the intersection of memory and timekeeping. In some sites, their houses are placed closer to communal structures. In others, they appear to have kept closer proximity to vantage points where horizon visibility was strong. The associations are modest but consistent. Where long-term observation of the sky was most easily achieved, we find spatial clues that imply designated observers existed among them. Distinct from earlier megastructures aligned to solstitial light, late Neolithic constructions begin to show architectural repetition. A community builds its central enclosure with a winter orientation. Generations later, when the original posts or stones fall, they rebuild the structure on the exact same line. This is not imitation by chance. This is the inheritance of knowledge. The builders no longer remember the first observer who chose that point on the horizon, but they trust that it was chosen for a reason that remains valid. Archaeology is full of these quiet traces of continuity. a rebuilt timber monument placed precisely on the footprint of an older one, a redug ditch following the arc of a prehistoric alignment, a consistent sightline running through hundreds of years of communal effort. Each is a testament to a dawning scientific consciousness, one that sees the return of light not as accident but as pattern. Comparative studies across regions reveal that this pattern recognition was not isolated to any one culture. In Northern Europe, alignments are often tied to landscape features that remain visible year-round, such as distant hills or stable shorelines. In the Danube Basin, researchers have connected settlement positioning to broader climatic cycles captured in fluvial deposits, showing that communities were likely aware of seasonal floods and their relation to sunlight cycles. In parts of the Caucasus and eastern Anatolia, long-term observation seems to have been woven into migration or transhumance cycles, with shepherding routes timed against the turning of the year. These are not myths yet. These are early scientific frameworks, emerging in different environments under similar pressures, daylight changing in ways regular enough to be trusted. The late Neolithic is also when symbolic systems begin to appear with greater frequency, but here we must move carefully. Not every engraving or motif is astronomical. Still, some repeated markings found on pottery, stone plaques, or wooden posts bear rhythmic spacing that mirrors solstitial intervals. Scholars debate whether these represent formal notations, but the frequency of the pattern suggests at least a deliberate attempt to organize time. Unlike earlier Paleolithic marks, which seem tied to animal cycles or hunting seasons, these later ones appear linked to a longer arc of observation, possibly representing communal rather than purely subsistence rhythms. In several well-studied settlements, such as those in the Orkney Archipelago or the Dordogne Valley, planners seem to have used older solstice structures as reference points when laying out newer buildings. This reuse of orientation implies that solstice knowledge had accumulated into a shared cognitive tradition. A generation did not have to rediscover the horizon. It was given to them, as reliably as the sunrise itself. Archaeological traces of repeated use at certain sites also suggest a ritual cycle supported by planning. Certain buildings or rooms were only opened seasonally, perhaps during the darkest weeks, consistent with the time when the solstice occurred. The rise of specialist roles is visible not through burials or tools, but through organisation. In settlements where household clusters fan out from central structures with deliberate orientation, it is plausible that a few individuals oversaw the layout. Some researchers propose that these organisers were not leaders in a hierarchical sense, but custodians of inherited spatial knowledge. Their task would have been simple and profound: to ensure that the old alignment was maintained, to keep the community oriented toward the turning point of the year. Their authority came not from power, but from continuity. This emerging structure is not yet cosmology. It is not narrative. It is recognition. The earth moves, the light moves, but they do so in a way that repeats. For a species accustomed to uncertainty, this was a quiet revolution. Predictability meant stability. Stability meant planning. Planning meant survival. And from this bedrock of repeated observation, the foundations of future symbolic systems would eventually rise. The awe that later cultures expressed toward the returning sun did not begin with worship. It began with recognition that the solstice behaved the same way every year, no matter who watched. Realization settled slowly across generations. Before stories could be told about the sun, people needed to trust its behavior, and they did. Through patient noticing, through incremental memory, through structures rebuilt along the same lines long after their creators were gone, humanity learned that the solstice was more than an event. It was a signal. It was structure itself. What we also begin to see in the late Neolithic archaeological record is the emergence of something that scholars describe carefully: intentional continuity. Earlier human groups adapted to their environments with remarkable flexibility, moving when conditions changed, shifting strategies when seasons demanded it. But by the 4th millennium before the Common Era, communities across several regions show signs of settling into patterns of life that echo the rhythms of the sky. This is not simply domestication, it is domestication of time itself. The solstice, with its predictable turning point, offered a kind of temporal anchor around which other activities could be organised, creating a quiet scaffold for social stability that left no written trace but shaped daily life all the same. In some settlements of this era, researchers note a new kind of architectural rhythm. Houses built along parallel lines, doorways angled with consistent orientation, courtyards shaped to catch or avoid seasonal illumination. None of these patterns require formal mathematics. They arise from memory and observation. A builder notices that light enters a room at a certain angle during the coldest weeks. A generation later, a descendant preserves that orientation, perhaps without fully understanding why. Over time, the cumulative effect is unmistakable. Repeated spatial choices made not for aesthetics alone, but for their relationship to the turning of the year. Long-term climatic data extracted from lake cores across northern Europe reveal that this period experienced fluctuations that would have made daylight particularly important to track. Small shifts in seasonal temperature bands influence crop viability, animal behaviour, and water availability. When the natural world changed in ways that were subtle yet significant, any community with strong pattern recognition gained an advantage. The solstice, being a stable astronomical event unaffected by local climate variability, served as the single most trustworthy point of reference. Even if a winter was unusually warm or unexpectedly severe, the position of the sun at its southernmost rise did not drift. It gave these communities a sense of certainty that the ground beneath their feet could not. Archaeologists also find indications that knowledge about the solstice was transmitted not only within settlements, but across regions through interaction networks. Exchange routes carrying pottery, stone tools, and other materials may also have carried ideas, including insights about solar cycles. When two widely separated communities construct buildings with similar orientations during roughly the same centuries, this may hint at shared understanding or contact rather than coincidence. The spread of these orientations cannot be mapped to a single cultural source. Instead, it suggests that several groups independently noticed the same pattern, and that some form of communication reinforced it. Knowledge, like the solstice itself, travelled. Evidence from certain communal structures shows that some buildings were intentionally remodelled rather than abandoned. This suggests that the solstice alignment was not merely a holdover from the past, but a feature that remained meaningful across generations. Archaeologists sometimes uncover subtle adjustments made by later builders to maintain a structure's original sightline as materials shifted or eroded. These corrections require someone to notice when the alignment no longer performed as expected. The presence of such modifications hints at a small but significant recognition. Accuracy mattered. As these patterns deepened, the communities involved likely developed a new sense of temporal identity. Instead of living only through cycles of hunger and plenty, they existed within a framework marked by fixed celestial events that connected one generation to the next. The solstice was not yet a sacred story, nor an embellished myth of light and darkness. It was simply the most reliable signal that the world offered, a guarantee that change unfolded in a recognizable sequence, and that the darkest point in the year did not last. This shift toward consistency created a foundation upon which later, symbolic systems could be built. Pattern recognition is the first step toward meaning making, even if meaning itself is not yet attached. The late Neolithic world did not interpret the solstice through the lens of spiritual birth or cosmological narratives. Instead, it recognized that the sky behaved with a rhythm that could be trusted, and that trust became a subtle cultural inheritance. This inheritance inspired confidence in planning, in marking time, and in building structures oriented toward moments that mattered. Before the solstice became a metaphor, it was a measurement, and before measurement became writing, it lived in the quiet minds of people who watched the horizon and understood that the world returned to itself. A human standing alone at the edge of a cold morning tens of thousands of years ago, looking toward a horizon that has no name, no carved marker, no monument, and yet carries the single most dependable signal that their world will ever offer. The landscape may be frozen tundra, or open grassland, or rocky shoreline. It may be a river plain in the Near East, or the foothills of a glacial valley in Europe. It may even be the high plateau of a region that will not see agriculture for many generations. The setting does not matter. What matters is that no matter where this person stands, the sun will rise at its farthest southern point, hesitate for a few days in a pause that only the most attentive eyes can detect, and then begin to turn back. Before any story, before any structure, before any shared language beyond the most essential sounds, the solstice was already there. It was the first reliable hinge across every environment humans would ever inhabit. When we speak of universals in archaeology, we do so with caution. Human cultures are astonishing in their diversity and shaped by specific histories, ecologies, and pressures. But the solstice belongs to a different category. It is not a cultural product, not an idea invented by a single community and carried outward through contact. It is a feature of the Earth's tilt, a predictable outcome of planetary geometry, and thus accessible to anyone with clear skies, a consistent horizon, and the patience to look day after day. That patience is something humans have always had. In the absence of clocks, books, and instruments, the only lasting certainty came from watching the world until its patterns emerged. The solstice was the first of these patterns, a celestial event that required no tools to find, only memory and attention. Anthropologists studying communities across a wide range of latitudes note similar tendencies in early observational behaviour. Whether a group dispersed seasonally or remained in more stable settlements, people learned to mark the turning points of daylight by comparing the length of shadows, the timing of dawn, and the angle at which sunlight touched the land. This is not inference. It is grounded in ethnographic parallels and paleo-environmental reconstructions, showing that seasonal awareness shaped foraging routes, winter preparations, and decisions about migration. The solstice's power came from its visibility. Unlike other celestial events that might be obscured or irregular, the longest night and the shortest day appeared every year with unwavering consistency. Even through changing climates, advancing glaciers, or shifting coastlines, the solstice remained a reliable measure. Geologists speak of stable horizons, the long, quiet lines formed by mountains or uplands that change at rates too slow for any human community to witness. These provided the earliest observational tools. As long as the horizon remained unchanged, the point where the midwinter sun rose or set would recur at the same place year after year. This geological stability allowed early humans in every region, from the Andean highlands to the river valleys of East Asia, to use the landscape as a natural record. Archaeology finds the evidence not in one site, but many. Repeated settlement positions, paths worn into hilltops facing specific angles of light, and viewing points where solstitial sunrise lines are unusually clear. None of these traces rely on symbolism. They reveal a simple fact. The people who lived in those places watched the sky because the sky was the one thing they could trust. When we compare early solstice indicators across continents, a remarkable pattern emerges. The methods differ, shaped by environment. In desert regions, people used cliffs and outcrops as precise light surfaces. In forested areas, the solstice line was found through leafless winter branches or cleared corridors that framed the horizon. In polar-adjacent regions, the sun's low arc created elongated shadows that acted as natural guides. Yet the underlying principle is identical. Daylight shifts predictably, and at the moment of greatest darkness, that shift pauses. This is the only astronomical pause that can be reliably detected with the naked eye in every known human habitat. Cross-cultural consistency arises not from shared myth, but from shared constraints. Every society had to understand when the cold would intensify, when food would become scarce, and when animals would migrate. The solstice was the earliest global signal that these phases were underway. The archaeological record shows that solstice recognition began long before the rise of monumental architecture. In Paleolithic caves, researchers study soot layers, entrance orientations, and the distribution of interior spaces to understand how sunlight entered certain chambers at particular times of year. In many cases, these caves were used over thousands of years, suggesting that communities returned not simply because they were sheltered, but because they offered a familiar relationship with winter light. In Neolithic settlements, alignments become more deliberate. Houses oriented along repeating lines, open areas configured to receive low morning sun, and communal paths structured around predictable illumination. What changes across these eras is not the solstice itself, but the complexity with which humans responded to it. One of the most striking aspects of solstice continuity is that it outlasts every cultural transformation. When societies migrated, they brought their memory of the sky with them. When climates shifted, the solstice remained visible as long as the horizon stayed clear. When new technologies emerged and settlements expanded, the need to understand seasonal cycles only sharpened. In some regions, communities ceased to build monumental structures, yet still oriented temporary camps toward midwinter light. In others, advanced architecture amplified the solstice into ceremonies or narratives, but always with the same foundation: the point on the horizon that marked the year's turning. What the archaeological and environmental evidence suggests is that before humans built meaning into light, they built accuracy. The solstice was the first shared measurement across the species, the first event that did not belong to any one group, but to everyone simultaneously. It did not require shared language, because its meaning was visible. It did not require shared belief, because its consequences, cold, hunger, the slow return of warmth, were universal. It did not require shared myths, because the pattern itself was enough. Realization moves gently here. Long before gods or cosmic stories, before symbolic suns of light or narratives of renewal, the solstice was a simple promise in the harshest season. It was the assurance that even in the deepest dark, the world would not remain still forever. The sun would rise again, and the path it traced across the sky would lengthen. People did not need myths to believe this. They needed only to watch and to remember. None. This is the final segment. Even in the most ancient darkness, humans learned to watch the same returning light, and in that patient watching, they began the long work of understanding the world.